Today is my pleasure to introduce the presenter, Dr. Rick Haasch. He's a senior research scientist at MRL. He's the manager of our OGER and XPS facilities in the MRL. Dr. Haasch has received his BS degree in chemistry from the Marquette University and PhD degree in analytical chemistry from the University of Minnesota. For more than 29 years, he has taught several hundred graduate students, postdocs in the use of XPS and OGER. He has been giving numerous lectures on the techniques across not only campus, but worldwide. He has recently served as a director in the American Vacuum Society. He is AVS, and he is currently serving as an editor of the AVS journal Surface Science Spectrum, SSS. He has published numerous research papers in the technique, in particular in novel battery materials. So without any further delay, thank you very much, Rick, for putting together this talk for us, for taking the time to deliver this presentation. You are a true resource for us in campus here. We are privileged to have you coming and giving this presentation to us. So with that, welcome, Rick.
Thank you. Thank you for that very nice introduction, Oro. So before I get started, for those of you who are not familiar with Central Illinois, this is pretty much what it looks like. So we have a lot of flat land and open land, so that makes it an ideal place for wind turbines. And besides the University of Illinois, the two other things that Central Illinois is famous for is corn, and the other is soybeans. Okay, so this talk is based more or less on a talk I gave in 2018 in South Korea. And South Korea pretty much does not look anything like Central Illinois. So it was a pleasure for me to travel to there and speak about the battery materials. So before I begin, I'd just like to acknowledge all the people that were involved with this research project. And this will also serve as a rough outline for the talk. And so I'll begin by discussing and introducing to you the various materials we'll be looking at for the batteries. And then we'll study some strategies for modifying the batteries in the second part of the talk to enhance their performance. And as you might imagine, much of this work has been supported by the U.S. Department of Energy, and we're grateful for their support. So the study of surfaces and interfaces involves pretty much every aspect of our lives. And in these examples, they all have one thing in common. They all involve advanced lithium-ion batteries. So what do these batteries involve? Well, the ones we'll be looking at today are the ones known as interpolation batteries. And so they consist of a lithium metal oxide at the cathode. And during the charging cycle, the lithium drops off an electron and then moves over to the anode where it intercalates between layers of graphite. And there it picks up another electron. And then during the discharge cycle, the lithium drops off that electron, moves back to the anode, or back to the cathode that is, intercalates between layers of oxygen, where it picks that electron back up again. And it's this ability to shuttle the electrons back and forth that allows this device to store energy and deliver it as a battery. So what does the battery look like inside? This is what it looks like in the microstructure. So besides the active oxide, there will be some super P, which is a type of carbon black, SFG, which is synthetic flake graphite. And this actually provides an electrical network that allows the electrons to be transferred between the current collector and the active oxide. And then to hold everything together is a binder of polyvinylidene difluoride. And so during the charging, lithium would move here. It passes through an ion-permeable insulating membrane. Most often it's polypropylene, where it intercalates into the graphite. So you can see here, these are graphite with the white edges, these big flakes, and then these black circles right here are the synthetic. These are actually the carbon black. And all this stuff that looks kind of like gum, that's the binder. Okay, so one part of the concept of the battery I'll like to introduce before I begin is what's known as the solid-electrolyte interface. And so this is actually very key in the performance of the battery. So like I said, we'll be looking at today transition-metal-oxides. And so these oxides will have a hydrophilic type surface. And so the SCI allows the oxide surface to build up a layer, an interphase that is, that somewhat mimics the solvent so that the lithium can move easily in and out. It also protects the coating and controls the wettability. And so how is this SCI layer formed? Basically, when the lithiums come back on the discharge cycle, two things can happen. The lithium can go in intercalate, pick up an electron, or the lithium can react with a solvent molecule and form an SCI layer, where it picks up an electron here. Unfortunately, in this case, the electron now is sort of trapped here. It can no longer participate in the charge-discharge cycles of the battery. So, and as you can imagine, throughout the lifetime of the battery, this SCI layer will continue to grow because we'll still have these two paths. And eventually, you might imagine that we're going to begin to lose capacity of the battery, and that's correct. And also, there may be issues with the layer becoming too thick. And I'll discuss some of those later. Okay, so what I'll do is I'm going to step back a little bit and introduce to you surface science. So how we define a surface basically depends upon the type of probe we have. So a lot of this talk will consist of XPS, which is one of the surface techniques. And that's an ideal technique because when we look at electrons, the wavelength of the electron is roughly the order of magnitude of the atomic spacing. So that allows a very nice particle to interrogate the material. So you can get a lot of information from that electron that is emitted. So XPS is a technique that's based on the photoelectric effect discovered by Heinrich Hertz and then described by Albert Einstein. And then later in the mid-1960s is made into a practical analytical tool. The experiment consists of X-ray beam, you irradiate a large area, and then we extract some electrons from a smaller area. And so how that works is the photon comes in, and that energy is absorbed, and then photoelectron is released. This photoelectron will be ejected with a kinetic energy that is equal to how much energy was put in, minus how much energy how much energy is needed to hold the electron to the nucleus, that is the binding energy. Normally, when we look at XPS data, we'll plot it on a binding energy scale, not a kinetic energy scale. So we basically just swap these two terms. So following this process, because we'll have an ion with a core hole, this ion will tend to relax and emit another electron known as an Auger electron. So on an XPS spectrum, we can see both Auger and photoelectron lines. And so the complementary process to this would be the emission of an X-ray photon. This would be basically X-ray fluorescence. So now I'm going to introduce to you another technique that is very common to the study of batteries. And many of you may not be familiar with this. And this is a technique known as AC impedance spectroscopy. It turns out that you can model electrochemical systems with electronic circuits comprising of common elements like resistors and capacitors. And so some of these components will be due to the solution, and some will be due to the electrode. So the electron components consist of a Faradaic impedance, which consists of a charge transfer resistance, and another component known as a Warburg impedance, which relates to the diffusion. We'll also have another component in the electrode, which represents the electrical double layer between the solution and the electrode. So that basically indicates that we have some polarization right at the surface of the electrode. So how do we use this? So if one knows the circuit diagram, one can actually solve the equations for that and actually use that to quantitatively model this spectra that you get. So sometimes, when we look at the electrochemistry at the low frequency limit, we'll get a 45-degree angle relative to the real and the imaginary axes of impedance plane. And this indicates the increased frequency right here. At the higher frequency limit, we'll see a spectrum that looks like this. It's just a semicircle. And then in most cases, you'll see both parts of the spectrum because we'll scan from low to high frequencies. Then you'll get the semicircle. So how can we use that to explain the performance of the battery? Here's some examples. And so case one is what we call a kinetically limited case. And that's where the charge transfer kinetics are very, very slow and inefficient. So we'll get mostly a semicircular plot with a small linear portion. In the case where the mass transfer is limited, that is, it is hard to get the ions to move from one electrode to the other anode, we'll see a mostly linear portion with possibly a small semicircular spectrum. And so in the case where both contribute, we'll see something like this. In certain cases, we'll get a double semicircular behavior. And this will indicate a series network, which you see here. And I'll give some examples of why this appears. So next, I'd like to introduce to you the family of materials that we'll be talking about today. And these are the NCM family, that is the nickel, cobalt, metal, manganese family of oxide materials. They occur in an XYZ = 10 composition. And so what we could do is by varying the amount of the component of each of the constituents, you can change the performance of the material. So for example, the very high nickel compositions of this oxide have high capacity. The medium compositions will have high stability, and the lower compositions will have lower cost. And so basically you tailor your composition based on your application. So in some instances, you may want a lot of power and a lot of capacity. So here's an example of the Formula E racing series. And so, of course, in a race car, you'll be worried mostly for performance. You won't be too concerned with the lifetime of the battery, because at the end of the season, you can see we'll have plenty of people here that'll help you buy new battery pads. But for the consumer, this may be a little bit too expensive. And so what you do is formulate a different composition where you can get a long lifetime. And here's an article about a professor, Jeff Dahm, that developed, based on the 523 synthetic flake graphite system, a battery that could last 1 million miles without needing to be replaced. So let's start with some characterization of the batteries. And so this is the NCM family of the raw powders. And so we can actually gain a lot of insight in terms of the aging characteristics of the battery just by looking at the raw powder. Because when the powder sits in its dry room, it's still going to be exposed to a little bit of moisture. And so it'll build up a hydroxide layer on the surface. What happens then is the lithium hydroxide can pull CO2 out of the air and form carbonates. That's pretty similar to what happens in an actual battery. So if we look at the different compositions, these are the high nickel constituents, the 811, 822, and then 622, and then we'll go down to the low nickel. And you see the metals all pretty much look similar. Where we see a lot of difference, though, is in the chemistries of the carbon and the oxygen. So here we see in the very high nickel compositions, we have a lot of carbonate formation as compared to the lower compositions. And this is also shown in the oxygen spectrum. In fact, in the highest nickel compositions, it appears that the this high binding energy peak actually exceeds the intensity of the metal oxide, or the metal oxide peak right here. So if you look at the ratio of the compositions, the high energy oxygen peak at 531 actually consists of lithium carbonate, and also metal oxides, mostly lithium hydroxides. And then having a lot of lithium hydroxide available at the surface makes the electrode prone to decomposition, because that's very reactive to the carbonates that are in the solvent. If you look at the compositions as they vary with the compositions as they vary with the family of the NCM. So the high nickel containing oxides tend to preside more at the surface than the lower ones. And so the manganese seems to occur much as we expect the composition to be. And then it appears then that cobalt resides below the surface. So it looks like the nickel is on the top and the cobalt was down below. And this will be important because this possibly indicates the mechanism of rapid decomposition by having excess nickel at the surface. So what does the oxide particle look like? You'll see that the oxide has a large primary particle that's made up of a number of smaller secondary particles. And it is engineered like this on purpose, so that the oxide particle has a large surface area, so that we can get a lot of lithium intercalating inside and out of the oxide. So you could actually go to Sigma Aldrich and buy this oxide, NCO, and make a battery with it. But because the material is just made for reagent grade material, it won't make a very good battery, that is. And so here, if we look at higher magnification, we can actually see here the other constituents of the oxide. The electrode, we see the binder right here, and some carbon black right there. And so often when you're studying the batteries, you do 2 types of tests. You do a calendar life test, which is a test where you charge the battery up to a certain level of charge, disconnect it, and let it discharge to a certain degree, then disassemble and study them. The other type of test is what is known as a cycle life test. That is, the battery is cycled until you get to some predetermined amount of capacity, and then disassembled and analyzed. And in each case, you'll see that we're developing a number of these little crystallites at the surface, and they're all localized. So it indicates that we're getting localized decomposition reactions at the surface. And eventually these crystallites will nucleate, form larger particles. And then, as you might imagine, that once these particles get large enough, the battery's probably no longer useful. And that's correct. And so if we look at the electrochemistry of the controlled aging, we can see that much of the impedance increase is actually at the cathode. Okay, and then at the anode, we'll see that both mass transport and charge transfer contribute to impedance. So this is pretty much like case 3 of the 3 examples I shown earlier. And at the cathode, this is case 1, where you're becoming charge transfer limited. You can't actually get the electrons back into the battery again. And so then if you look very closely right down here, you actually see the double semicircle appearing. So that's the case 4 I showed you. So let's look at some of the XPS from these new batteries. And so on the bottom here is a fresh battery. And so this is the battery just upon assembly, where you take a slurry of the oxide, the binder, and the carbon black, and basically paint it onto the electrode and on the current collector and let it dry. And so the battery is not going to behave very well initially after assembly. So what is done is what are known as formation cycles. And then this is how you develop, you clean off the, maybe the surface oxide that's on the particles during initial formation, and then form the SEI layer. And then by looking at the change in chemistry, we could see that the metal oxide peak is pretty much attenuated. So we have a nice, fairly thick coating, at least in terms of an electron emission, fairly thick coating consisting of carbonyls and carbonates. And then we also indicate that there is an increase in the phosphorus signal. So in this electrode, the electrolyte is what's known as lithium hexafluorophosphate, or LiPF6. And so we're seeing that it is actually deposited upon the oxide as well and participating in the SI layer. Okay, and then here's a comparison of the formation cycle and what's called an accelerated aging test. In this case, the battery is held at an elevated temperature and held at a high state of charge to simulate charging of a battery. You can see now that the oxide signal compared to the carbon is greatly increased. So we're actually covering up much of the electrical network that is the graphite and the carbon black, and covering it with some type of an oxide. It looks like carbonates and hydroxide. And then we can also see that the phosphorus signal has been greatly increased. And this pretty much indicates why you should not leave your laptop plugged in all the way, because if you hold your battery at a high state of charge for extended periods of times at elevated temperatures, you're just accelerating the aging and you're taking life out of the battery. So next are some examples of SIMS, of some fresh and formed samples. And basically, there's not a lot of difference between these two. Basically, much of the change you see is some of the age samples, the calendar life aging cycles. You'll see that this is actually an anode instead of the cathode that we described before. You see that there's a buildup of manganese at the anode side. And this indicates that there's manganese dissolution at the oxide surface, and it is being transported to the anode. And this is not good for the battery in that it is going to stick to the anode on the anode's SEI, be trapped there, whereas during the charging cycles, when the lithium is shuttling towards the anode, it's going to pick up the lithium. It's going to form a side reaction where now that lithium is trapped at the anode SEI, and it can no longer pick up an electron from the anode, from the graphite. And so now you no longer made that lithium active, so you're reducing the capacity of the battery. So in the next section of the talk, I'm going to describe a couple of different strategies that we have for trying to minimize that effect. In the first case, here is an example where some researchers modified the surface of the electrode, the positive electrode that is, with ALG alumina. And so they found that a coated sample had an 89% capacity retention as compared to the uncoated sample. And so they also noticed that there's a minimized cobalt dissolution in this case because of the coating. And you can see here that the differences in impedance with the cycling. So the bare are these little dots, and the uncoated, well, the bare is this one, and the coated are these, excuse me, the blue is the coated. And you see there's not a lot of increase in the impedance. Then another group studied NCM material, and they also noticed an increase in the capacity. But then they also noticed that after heating, there's some interdiffusion between the atoms in the alumina layer. That is, it looked like both the manganese, nickel, and the cobalt signals were all increasing after the high temperature treatment. So it looked like the material, the metal oxides, the transition metal oxides that actually are reactive and prone to dissolution will eventually move back to the surface. So the next section is a group of experiments that, together with Argonne National Laboratory and the University of Illinois, we did some studies of the more advanced high manganese containing NCM. And so just to remind everybody, alumina, the ALD process, the surface is dosed with trimethyl aluminum, where it reacts with the hydroxyl at the surface and gives off methane byproduct. And then and this is self-limiting, then we add another layer of water vapor, form hydroxides, and then repeat with trimethyl aluminum, water vapor, trimethyl aluminum, and so on. And so on. Now I'm going to step aside a little bit and introduce to you a method for determining surface thickness. And so what we would like to do in our study is determine how the thickness of the alumina layer reacts to the performance of the battery. And so if you use the Beer-Lambert relationship, which describes the attenuation of the electron as a function of depth, you'll see that we'll get this exponential decay. And then we can actually use this equation to develop a model to estimate the thickness. So what we'll do is we'll develop a two-layer model, and then we'll form an equation for each layer, integrate, and we'll come up with an equation here that we can use the intensity to estimate a thickness. So the first thing we wanted to do in our case was determine a way to actually estimate the thickness on the electrode. So as you might imagine, the surface of these electrodes is definitely not two-dimensional planar. They're very rough and sort of like a mountainous type surface to the electrons. And so what we did is we developed a method where we would, during our ALD deposition, we would co-deposit together with our cathode. We'd put a silicon wafer next to it, and then we'll get a nice planar surface, and then we'll pull those both out and do some analysis. And so what we'll do is we look for a signal that we could relate to the thickness of the silicon on the silicon wafer. So if you look at the ratio of the aluminum plus oxygen to the carbon, we found a region where the two of them were linear. So we could come up with a way that we could use this factor right here to relate it back to the thickness on the silicon wafer and get an estimate of the planar thickness that aluminum oxide would be. And so here are some XPS examples right here of the deposition. You can see, in fact, when we are depositing the alumina, that we are attenuating the carbon signal. We're building up an aluminum signal and also the aluminum oxide signal. And so one thing that surprised us, but after thinking about the chemistry a little bit, it shouldn't have surprised us, that we actually were coating the binder. But we realized that aluminum, probably in the trimethyl aluminum, is pretty reactive to the fluorine in the binder. And so here's some SEM and EDS images of the coated surface. We'll see here's what the surface looks like. You can see the binders kind of glowing like these little gumballs. Here's some carbon black. So you can see the carbon black in the carbon signal. And then you can see here that the alumina deposits pretty uniformly. And because the binder is pretty uniform throughout the layer, it was pretty uniformly coated as well. So once we started studying the performance of these batteries, here's shown the initial charging capacity of the battery in the bold black, and each of these are increasing thickness, or I'm sorry, decreasing thickness. So we see that after 50 cycles, we have limited capacity as compared to the increased thicknesses. And you see the normalized capacity shows that as well. For the thinner layers, we found that we have less capacity overall as compared to the thicker layers. In fact, the thickest layer showed after 50 cycles a very minimum decrease in capacity. And then the AC impedance shows the initial cycles right here. Show very low impedance, which we were happy. This is actually a little bit lower than we expected. And then after 50 cycles, we see that the thickest layer had the least amount of capacity or impedance increase. The higher had a little bit more, then a little bit more, and then finally at the uncoated, we had a lot of impedance increase. And so if you notice right here, this is a good example of that double semicircular behavior. And this lower semicircle indicates that we think we're beginning to break down the electrical network of the system. And that is, we're beginning to coat the graphite and the carbon black. So now we're not able to shuttle those electrons from the oxide particle to the current collector. And so now this system is no longer very useful as a battery. So this battery would be pretty much used up. So looking at the XPS, these are comparison of 0 and 50 cycle of, so 0 nanometer before and after 50 cycles. We can see that we're getting coating and increase in the carbon signal. So the carbonate signal from the oxygen. And so we're also notice that we're getting a little bit of diminishment of the manganese. So eventually after 50 cycles, we are starting to lose some manganese. And this is a comparison with, so this was an uncoated, this is coated. So before and after 50 cycles. And so one thing we can notice that's very, very interesting is that the chemistry of the coating is different. We see that in the alumina coated material, we have a pretty intense carbonyl signal that we didn't really see in the uncoated. So it indicates that the chemistry actually of the surface of the material is actually important in terms of the behavior and the performance of the battery. So this is just a comparison that here we see the differences between the cycles. We have a lot of carbonate in this case, and in the coated we don't have a lot of carbonate. So in this case, mostly because the nickel is now moving towards the surface of the electrode, we're getting some oxidation or some reduction, I mean, of the carbonate at the surface. And this is a comparison of the SIMS of the negative electrode that we see in the unmodified, the modified cell right here. We got a lot less of the migration. So this, in the uncoated film right here, we see that the depletion of the manganese goes pretty deep as compared to the depletion in the coated. So what we found here is that the alumina coating does initially prevent the dissolution of the metal, but eventually it'll break down. So in the next examples, I'll show some oxide electrodes. In this case, it's just LMO, lithium manganese oxide LMO, that is coated with a variety of different self-assembled monolayers. And so these monolayers were fabricated to have different chemistries. And so, as I mentioned earlier, that the metal oxides will have a hydrophilic natured surface. And so we picked a variety of SAMs that had both hydrophobic of different types and a hydrophilic variety. And so also we varied the chain length and also the functional group, substituting fluorine for hydrogen. And so here's just some quick XPS to demonstrate that we are actually, when we change the length of the, for example, the hydrocarbon type SAMs, we are actually increasing the carbon signal. Then we see when we have the fluorinated carbon, we are seeing the indication of the fluorine. And then for the polyether, we actually didn't see much. And so this signal, because it's so low, indicates that either we didn't get a coating, or if we did get a coating with this SAM, it just fell over. And that would not surprise us, because the polyether has a hydrophilic type chain. It might just tend to fall and stick to the surface of the oxide. And so one of the things we wanted to check in the study is the charge transfer kinetics. And here's, if you're familiar with electrochemistry, the Nernst equation, which will describe this plot. So what we wanted to look at is the charge transfer. Okay, so this is represented by the difference between this part of the curve and this part of the curve, the delta E right here. So on a one electron transfer, which we were using the oxidation of ferrocene, which is a one electron process, to simulate the charge discharge in a battery. And so ferrocene is a fairly large molecule, so we'll actually study the effect of the SAM on the interdiffusion of some larger molecule into the SEI layer. And so in a one electron process, this separation should be 59 millivolts. And so if the charge transfer is reduced, this separation should increase. And so here we are. We're going to now compare the effective thickness of the different SAMs, the alkyl groups, and the fluoro and polyethers. And so this first plot right here are a comparison of the two-layer model calculations. And so we see as we increase the alkyl chain length, we get a pretty linear increase in thickness, which is good. That would suggest to us that the SAMs are standing up like they should. Then if we look over at the coverage, they all, in all respects within the error margins, have the same amount of coverage. We will notice though that the fluoroether, the fluorinated alkyl, has about the same thickness, which they were both 10 alkyl chains with the hex, well, actually it's a 10 atom chain, just like the 10 atom alkyl chain. But we'll notice that even though it has the same thickness as we expected, it didn't have the same coverage. And that's because the fluorine is a little bit bigger than the hydrogen. And so we had a little diminished coverage right here. So one thing we also noticed, which was echoed in the XPS spectra, is that the effective thickness of the polyether, as well as the coverage, were much lower than expected. Okay, so if you look down here, these are the differences in the delta E, or that is the amount of charge transfer. This is the pristine LMO. So the default value for the delta E would be about 150 millieV. So we could see that we do increase the delta E value. That is, we decrease the ability to do charge transfer by putting the SAM on the surface. Okay, we could see here that the polyether did not very much increase the delta E. So we're getting about the same amount of charge transfer as the bare LMO. And this is another kind of confirmation that it doesn't look like the polyether is making a very thick chain. If we look at the impedance right here, we see that we'll get the largest amount of impedance from the tallest sample, which are expected. Also, so the hexadecal is a 16 chain length. The fluoroether, the fluorinated alkyl, also has a high impedance, even though the coverage in this isn't as high as the alkyl 16 chain length. Because fluorine is larger, it's harder for the ferrocene to diffuse in and actually interact with the LMO. Then we can see that pretty much the polyether and the pristine LMO look identical. So here's some comparisons of the contact angle measurements with the and the salvation energy. So these are some examples of some common solvent electrolyte compositions. And so as I mentioned, metal oxides will have a hydrophilic surface. And so we want to study the effect of wetting. Okay, so you can see that the polyether, the polypropylene carbonate wets very well. And as you can see that it has the lowest salvation energy. And so you can see we'll have an increase in the contact angle for each of the increasing chain length alkyl groups, BPA, DPA, and HDPA. It looks like the DFPA, the fluorinated, has the highest. So it's probably the most hydrophobic of the solvents that we have. Next, we have a more common combination, the ethylene carbonate dimethyl carbonate system with the LiPF6. This is what most of the examples I showed earlier in the talk used as the solvent system. We can see we get a pretty linear increase in contact angle with increasing alkyl chain length. We see the contact angle is once again the greatest with the DFPA. And again, the polyether is the lowest because it is wetting very well. And so in this case that we see that we'll get the, here we're looking at the amount of dissolved manganese as determined by ICP-MS. We can see that the thickest alkyl chain, that is the one with the longest chain length, attenuates the dissolution of manganese the most. As you can see, the fluorinated alkyl is about the same as a 10-member alkyl. Polyether had the most, so it proved to be the least effective in terms of preventing the dissolution of the manganese. And so here's some examples how you can then now come up with schemes so you can tailor the amount of wetting to maybe vary the performance of the battery. Maybe you'll want to make them very high performance at the beginning and then make them, or have some that have a more extended lifetime. Okay, so what we demonstrated with this section that the SAMs did allow the lithium transport back and forth, and then also prevent the dissolution of the manganese. So what I'll do now is, in the interest of time, I'd like to conclude and look forward to the day when we can all get together and come to talks together. And so with that, I'd like to remind you of next week's seminar, which is an introduction to focused ion beam by Hongwei Zhou. And then if you'd like to contact the XPS staff, you can email either me or Mohammed. And with that, I'd like to thank you for your attention, and I'll be happy to answer any questions.
Thank you very much, Rick. Just a reminder to everyone that this is the second talk that Rick gives in this webinar series. Early in this series, he gave a talk about on an introduction to XPS as a technique. You actually can find that presentation in our YouTube channel as well. Now going to the two questions here, Rick. One question is for slides number 26 and 27, where you give some materials composition as measured by XPS. The question here is, did you actually do surface sputter cleaning for such measurements? If yes, how much are you sure about the percentage of oxygen, since the sputter oxygen actually goes back to the surface due to the high reactivity?
So no, these are not sputtered because we didn't want to sputter these because that would alter the chemistry as well, besides preferentially removing light atoms and everything else. And so the sputtering can be quite reactive, and it can actually cause reactions.
Okay, as a follow-up to that question, I have one here myself. I mean, what is the general precautions one needs to take when handling the samples? Do they need to come like on an inert atmosphere before being loaded in the XPS chamber? I believe you talked about that, but can you give more details?
Yes. They usually are brought to the XPS in an inert atmosphere, but fortunately for these materials, that if they are already aged, they are not very reactive, and so you can bring the samples to the instrument in the sealed mason jar that you took out of your glove box, and then I can have everything all set up. And then we'll just open the jar, put the sample on the holder, and get it pumping within a matter of 5 seconds. We found that that works very, very well. That'll even work for lithium metal. I've done it with that. Because even sitting in a glove box, a piece of lithium metal will have a passivation layer, so that as long as you don't start scratching the surface of the lithium, you won't really cause any issues.
I see. Okay. All right. One more question about quantification of the species here. If we want to quantify the material loss, for example, manganese loss from the battery electrodes after cycling, wouldn't the XPS just give signal from the SEI? Or is there any mode that can selectively give signal from the electrode below SEI so the quantification can be done? I guess the question is like how well can you localize the information you are getting regarding the manganese loss, for example, in the material?
Okay, let me go back. And so we actually did not look at the manganese loss by XPS because when the batteries are actually aged, it's almost impossible to see the metal signal. And so if this is what the person is referring to, so in this case, we looked at the solvent from a cycled battery and studied by ICP-MS. And so by looking at how much manganese was dissolved in the solvent, that was how we estimated the amount of manganese that was lost from the cathode.
Okay. Well, I have one final question here, is that in some of these slides, when you put like cycles of the tests that were done, were these done what they call the accelerated tests, or it was just normal use of the battery?
Okay, so let me see. Some of these, let me go to a good case right here. The ones at least I showed with some of these were actually accelerated aging tests. And so my other tests, I'm guessing that they were, for example, this one. This is just ordinary uses of the battery, so they're just cycled back and forth.
I see.
So this would be what we call we'll just cycle life test.
Okay, I guess the question is that there is no you don't expect any difference between like accelerated test versus
the accelerated test is just like you basically cycle it more. But so you do that so maybe you can do a test in 50 cycles that might take 150 cycles.
Yeah. Okay. And I think some of the researchers from Argonne have been here showing photographs of the setup they have there. All right. I do not have, okay, there is one more question that popped up here. Nickel and cobalt form a solid solution, right? Is there any way to tune the cobalt to nickel ratio to improve the battery efficiency?
Okay, so I'm not quite sure about the solid solution because these are oxides. It's not a metal system.
Mm-hmm.
And so basically what they're doing is they're taking mixtures, at least in this case, of different, they'll take a certain amount of, let's say, LNO, so lithium nickel oxide, and then lithium cobalt oxide, lithium manganese oxide. So basically you'll have, in this case, the 821, you'll have 8 parts of the LNO, and then 1 part each of the LCO and LMO. So that's basically how, and then they mix them together and then they produce their battery. So does that answer the question?
Okay, the same person who asked about the manganese loss is trying to explain better here the question. Can we actually do quantification of his species lost other than metals, such as oxygen, after cycling? Or that's not possible at all using XPS?
Let's see. Well, you can quantify. So you can look at the individual components, if that's what the person's asking, and study how they change.
Okay. Right. And one more question here is for the manganese dissolution, which by using the ICP-MS method. Usually, how much amount of cycle active material is required? You know?
You mean?
So when you are going to study the manganese dissolution, I think you showed a slide there with ICP-MS. Do you know how much of the material that's being cycled actually required for that analysis? I believe that's the question.
That I don't know, but most of this work is done in coin cells, and so it's the amount of solvent that the grad student that was doing this work was able to extract from the cell was enough for the ICP-MS. ICP-MS is very sensitive.
Okay.
And so in fact, they probably even had to dilute it a bit.
All right. Well, I guess that's all the questions we had here. Again, the previous presentation from Rick on basic XPS is already posted in our channel. This presentation will be posted within a few days or so. If any of you would like copies of these slides, you need to please contact Rick directly. See if he will be willing to share those. With that, I would like to invite you guys to come back next week for a talk on focused ion beam, which is by far one of the most heavily used techniques here in the MRL, in all the facilities I know around the country, for electron microscopy sample preparation and also for fabrication of 2D and 3D materials as well. So again, every Thursday, noontime, here in the same place, and you can register for that going to our website. So with that, any more comments, Rick?
No. Thank you for everybody's attention. I hope you enjoyed the talk.
All right. So again, thank you, Rick, for the time, for giving this exciting presentation and this very timely topic. So I guess with that, thanks again, everyone. I hope you guys stay safe. See you guys next week. Take care. Bye-bye.